Today is our last lecture on descriptive statistics. And what we're going to focus on today is actually going to act as a bridge between the topic of descriptive statistics and what we will be moving into next day, which is our inferential statistics. How it is we take the results from our sample and make meaningful and correct conclusions about that larger population. So let's launch into this topic of z-scores and probabilities. Let's try that. There we go. Okay, and I'm going to start with a thought question here. Mike scored 172 on his recent history exam. Is Mike a good history student? What do you think? Go ahead and get your reef system out. What do you think? Is Mike a good history student? Give you about 10 more seconds to get onto that system, which should be going before class, and let us know your thoughts. Okay, I think I'm going to go ahead and stop it there. Looks like we have a pretty good consensus. For the most part, you are in agreement that you really just don't know. And I would agree with you. You are missing some pretty vital information here. What else would you want to know to determine whether Mike is a good history student?
You would need to know either whether the 172 represents a percentage or what it's out of.
Okay, so you definitely would want to know some context, like what that 172 is out of. Is it 100, like a percentage? Is it 200, which still sounds pretty decent? Is it 500, in which case Mike is probably in trouble? Okay, so that would be one good piece of information. What is the exam out of? Is there anything else you might want to know?
What scores did other students get, so you can tell whether or not it's not just him who got that score, it's like an average score.
How's he doing relative to everybody else? Thank you, Alex. So even if that 172 is out of 200, if the average was 195 and he got the lowest score in the class, you're probably not going to conclude that he's a good history student. On the other hand, even if the exam is out of 500, if the average was, say, 120 and he got one of the highest scores, that's something different altogether. So this idea of putting scores into context is really what z-scores are all about. And that's what we're going to talk about today. So we did this what more do you need to know piece already. We'd want to know both what it's out of ideally, but also how did others do? How did you do relative to others? And z-scores are really going to help us to answer that question. So a z-score is a score that's expressed relative to the mean in standard deviation units. So it's going to tell us both how a student did relative to what was average, above versus below, and how far was that student in average in these standardized standard deviation units. Now it's fairly easy to calculate once we've calculated our mean and standard deviation. So in order to transform data into z-scores, what we do, let's do the sample version first, although these two formulas are equivalent. We take that person's score, we subtract the mean, and we divide by the standard deviation. So if we've calculated our mean and standard deviation, we're good to go. For our population data, we would do exactly the same thing. We just use different symbols to designate that we do in fact have a population mean and a population standard deviation. So here the formula looks different, x minus mu over sigma, but it's the same calculation. It's the difference between the score and the mean divided by standard deviation to put it into those standard deviation units. Okay, now here's how we interpret them. The sign indicates whether the score falls above or below the mean. So if you wind up with a positive z-score, it's because, well, score minus mean, so that's going to be positive if the score is above the mean. So a positive z-score indicates that the score you are looking at was above the mean. A negative z-score indicates that the score you're looking at was below the mean. X minus mu or X minus m for sample mean. So if the score was lower than the mean, that will be negative. So the sign tells us above or below. And then the absolute value of the z-score indicates how many standard deviations the score is from the mean. So if the absolute value is larger, then the score is farther from the mean. If the absolute value is quite small, that means the score is fairly close to the mean. So let's do a couple of examples here so we can kind of start to understand what these z-scores are showing us. So here's the first one. On a recent psychology exam, the mean score was 80 with a standard deviation of 5. Lewis, a student in the class, got 70 on the exam. So here's how we would calculate his z-score. So the formula, we're going to use the population formula since we would know all of the scores within the class. So we would in fact have population data. So X minus mu divided by sigma. Our X here, the score we're looking at, 70. The mean is 80. The standard deviation is 5. So if we plug those numbers into our formula, and yes, I have chosen easy numbers to work with here, we would find that Lewis has a z-score of -2. Notice that these scores being whole numbers, that would actually be the exception, not the rule. So don't think you've made a calculation error if you do wind up with some decimal places. I've just chosen easy numbers to work with. So Lewis's z-score for the psychology exam was -2. What that's telling us is that Lewis scored 2 standard deviation units below the mean on the psychology exam. So not only was he lower than what was typical, what was average, but he was pretty far below the average when you scale it in these appropriate units. So that's what z-scores can tell us, 2 standard deviations below the mean. It's giving us context to understand that score. Let's do another one. On a recent biology exam, the mean score was 60 with a standard deviation of 10. Lori, a student in the class, got 70 on the exam. So if we wanted to calculate her z-score, we would use that same formula, X minus mu divided by sigma. Again, I'm using the population symbols here because we would know the scores for everybody in the class. We would have that population data. And we would see that 70, the score, minus 60, the mean, divided by 10, the standard deviation, would be 1. So Lori's z-score for her biology exam is 1. Can somebody give me the interpretation here? In fact, let's have you all give me the correct interpretation here. Lori's z-score of 1 indicates what? What does this tell us? Does it mean that she's 1 point above the mean on the biology exam? 1 point below the mean on the biology exam? 1 standard deviation unit above the mean on the biology exam, excuse me? 1 standard deviation unit below the mean on the biology exam? What is this telling us? Five more seconds. Okay, let's take a look at where we are here. Looks good. Yes, that z-score of 1 does in fact indicate that she scored 1 standard deviation unit above the mean on the biology exam. Now here's what I want to point out. Lewis got 70 in psychology. Lori got 70 in biology. Same score. But in those two cases, they're indicating very different levels of performance, which we can see when we do this transformation into z-scores, because it puts those scores in context. Lewis's 70 was pretty far below the mean on his exam. Lori's 70 was above the mean on hers. Same score, but very different interpretations about the quality of that performance. So that's what z-scores can do. They really put things into context. Questions so far? Okay. Then let's continue with our understanding of z-scores. If we convert all of the data in a sample or population to z-scores, then the distribution of z-scores will have a few properties that will always be in common. So one property is that the mean of all of the z-scores within that distribution will be 0. Some scores are above the mean and will cause positive z-scores. Some scores are below the mean, will cause negative z-scores, but it will all come out on average to 0. So if you convert every single score to a z-score, then that distribution of scores will always have a mean of 0. Moreover, because of how we've created these z-scores, the standard deviation of that distribution of z-scores will always be 1. So the mean is always 0 of a z distribution. The standard deviation is always 1. And that's just because of how these scores are created in the first place. Something else to know, however, is that the z-score transformation, transforming every score to a z-score, does not change the shape of the data. It does not change the shape of the distribution. So if you start out with a positively skewed distribution and you transform every single score to a z-score, you will still have a distribution with a mean of 0 and a standard deviation of 1, but it will remain positively skewed. So this doesn't change the shape of the distribution, it just normalizes the mean and the standard deviation. So why would we do this? What are these z-scores good for? One thing is that an individual z-score can be meaningfully interpreted. As I just showed you, that score is telling us where the individual falls within that distribution of scores. Are they above average? Are they below average? How much above or below average? It helps us for that meaningful interpretation by putting that score in context. It also allows for easy comparison across different distributions of scores. So let's say if we're trying to figure out if a student, an individual student, is better at psychology or biology. They're considering both of these majors. In which direction should they head? Well, we can't just directly compare the grades because they do come from different distributions of scores. So to understand where the student's talents lie, we could convert their scores in each class to z-scores and then do a direct comparison. If they have a higher z-score in one subject than the other, that means that relative to everybody else, they're stronger in that area. So it really allows us to compare across different distributions. Now there's one more thing as well. Remember that the z-score transformation does not change the shape of the distribution. However, if the scores started out as a normal distribution, a symmetric bell-shaped distribution, then we can calculate the probability of a score's occurrence. In the pre-lecture I posted to your class webpage, I gave you a little introduction to probability, or really probably mostly a reminder about probability ideas that you had learned in the past. Now we're going to link everything together. So if you recall from that pre-lecture, I kind of finished it off showing you a frequency distribution of scores and how we could figure out where a score fell within that distribution and calculate a percentile rank. What percentage of scores fell at or below that score? Z-scores can be used to do that same thing if the scores came from a normal distribution. So here's the big picture idea. We're going to talk about probability distributions. So this idea of taking scores from a class where we have the entire population of scores, it's kind of the exception rather than the rule. In real world research, we rarely have access to all of the scores in a population. But we might want to figure out where a particular score falls within that theoretical population to which we don't have access. And that's where probability distributions come into play. They describe the probabilities of receiving different scores in a population of scores. So a normal distribution, and I think this is the first class in which I've used this definition, a normal distribution, which is a symmetric bell-shaped distribution, can be used to represent many characteristics of the population. For example, IQ. IQ is normally distributed. Anxiety level is normally distributed. Most people fall somewhere in the middle, but there are people who are more anxious and people who are less anxious. We have this bell-shaped distribution. Creativity is known to be normally distributed. Most people are somewhere in the middle, but there are more creative people and less creative people. Aggression level is normally distributed, and we can go on and on. Many characteristics of the population do in fact follow a normal distribution. So the shape of this distribution, it is symmetric around a mean. It is unimodal, there's just one hump, and it does have this very distinguished bell shape to it, where most scores are right in the middle, and then in either direction, they kind of taper off. With a normal distribution, we know everything we need to know about where scores fall if we have just two parameters. All we need to know about a normal distribution to know how the scores in general fall is the population mean and the population standard deviation. Those two parameters capture everything we need to know about the normal distribution. So let's connect this up to z-scores. Z-scores, we know the distribution has a mean of 0 and a standard deviation of 1. So a normal distribution can be described using any mean and any standard deviation. If I give a test and my scores are normally distributed, maybe the mean is 80 and the standard deviation is 10. But if I convert all of those scores in this distribution to z-scores, and it was normally distributed to start with, remember, the z-score transformation doesn't change the shape. But if those scores were normally distributed to start with, and I convert all of the scores to z-scores, I would wind up with a standard normal distribution, which again has the same bell shape to it, but the mean is 0 and the standard deviation is 1. And since variance is standard deviation squared, the variance would also be equal to 1. for the standard normal distribution, the distribution of z-scores. I realize that you probably are not quite sure yet of where I am heading with this, and that's okay. I'm going to get you there. But are there any questions on the content so far, on the ideas I've presented? Seeing nothing in the chat box and hearing nothing from the room, let's go ahead and see how these ideas do connect with one another. Think back to the pre-lecture. If we have a frequency distribution, we know where all of the scores in the distribution fall, we can figure out a percentile rank. What percentage of people fall at or below a certain score, for example? We can also use the standard normal table to find probabilities and percentiles. Now, before I go into this example, I want to emphasize that to do this, you have to know that the scores are normally distributed, or at least be able to reasonably assume that the population scores are normally distributed. So here's an example of what we can do with this information. IQ scores are normally distributed with a population mean of 100 and a population standard deviation of 15. Let's say Brianna has an IQ of 120. And if there is a Brianna in the class, I'm not picking on you. It's just a name I chose, although 120 is really good. What is Brianna's percentile rank? That is what percentage of people would score the same as Brianna or lower on an IQ test. We have the ability to figure this out using z-scores. So here's how we do it. Let's start by identifying the information we're given in the scenario. Population mean is
100.
100. Thank you, Mackenzie. And Mackenzie, I'll let you continue. Population standard deviation is
15.
Thank you. And the score of interest that we're going to work with here is
120.
120. Excellent. So Brianna's score that we're going to use to do our percentile rank calculation is 120. The population mean that we're given is 100. The population standard deviation is 15. So the first thing we want to do after identifying the information, so I guess that's the second thing we want to do, is convert the score of interest to a z-score. Now we are making assumptions about the mean and the standard deviation in the population, so we'll use the correct symbols and we'll plug in the numbers we just identified. So to calculate our z-score, we do 120, the score of interest, minus 100 divided by 15. And we plug that into our calculator and we find that it is 1.333333. We'll round to 2 decimal places, 1.33. Now again, notice that z-scores are rarely whole numbers. I just chose easier examples to start with. So just from looking at this, we can already see that Brianna is a good bit above the mean in terms of her IQ. But now what we're going to want to do is figure out what percentage of the population would have a z-score of 1.33 or less. And here's how we do it. So we're going to find the probability associated with a z of 1.33 using the standard normal table. Now, there are many versions of this table online, but I've attached a version at the back of your lecture outline. So you have this table in your notes. And for those of you who are wondering, yes, if you need this on an exam, of course, I would provide the table to you. You don't need to try to memorize this. Not that you could if you tried. So here is what the standard normal table looks like. And it, of course, continues on down, but this is at least the beginning point. So what we have here down the side is the z-score to 1 decimal place. So we first will want to identify the z-score we have to one decimal place. There it is, 1.3. And then across the top, we have the second decimal place. So our score was 1.33. Here's the 0.03. We simply need to find the convergence of that row and that column. So the probability we're identifying from this table is 0.4082. Now, to utilize this number, you need to understand what it's telling you. As it says at the top, the table values represent the area or the probability of falling between the mean and the z-score that you've looked up. So let's put this back onto the little diagram in our notes. So what this number is telling us, this 0.4082. So here is a z of 1.33. It's above our mean. And what we're trying to calculate is this area below a z of 1.33. So if you think of the area under the curve as 1 or 100%, the proportion of scores, the probability of getting a score of less than 1.33 would be this entire shaded area. Now, what the z-score we looked up is, it's the distance, the area between the mean and the z-score we've looked up. So this region in here between the mean and the z-score of 1.33 is 40.82% of the entire area under the curve. But we want not just this chunk of the curve, but the entire probability below that z of 1.33. So what could we do here to figure this out? Any ideas?
Wouldn't the probability that's left to the mean be like 50%?
Exactly. The curve is symmetrical. So half the curve, 50%, falls below the mean. Half the curve, 50%, falls above the mean because the curve is perfectly symmetrical. So that area below the mean is 0.5, 50%. So to figure out the probability of getting an IQ below 120 or a z-score below 1.33, we take 0.5, which gives us the left half of the curve, and we add the 0.4082 that we looked up in the table, which tells us the area between the mean and the z-score. And we find that together, this is 0.9082. Does everyone see how we got that? Okay. So what these calculations have shown us, if we want to interpret the probability, is that Brianna's percentile rank is 90.82%. I've just multiplied by 100% there. That is about 91% of people have an IQ score of 120 or less. So by calculating the z-score and then figuring out the probability associated with that z-score, we can really put that score in context. Her percentile rank is almost 91% with that IQ score of 120. Questions there before I go on to a second example? I hear a microphone off. Is there a question? Perhaps you changed your mind. I'm not sure where that was, so I can't call anyone out. Okay, let's try another example and see how all this comes together. So here's my second example. SAT scores are normally distributed with a population mean of 1,000 and a population standard deviation of 100. Sean scored 950 on the SAT. what is Sean's percentile rank? So we're going to start off in exactly the same way by identifying our information. Here, we have a population mean of 100, a population standard deviation of, a population mean of 1,000, I can speak, a population standard deviation of 100, and a score of interest, Sean's score, of 950. So once again, we need to calculate our z-score for Sean using the information that's given to us in the problem. So here we go. For our z-score, we take Sean's score of interest, 950, minus the mean, 1,000, divide that by 100, and we plug that into our calculator, and we find that Sean's z-score is negative 0.5. Okay, negative 0.5. Now we need to look up that score in our standard normal table to figure out the probability associated with negative 0.5. So here's our standard normal table once again. There are no negative numbers in it. What do we do?
Would you just use the positive numbers and then whatever the intercepted number, make it negative?
You would use the positive number, but you don't want to make the intercepted number negative because it's still a probability, and probabilities are always going to be positive. But you're right in thinking you can just use the positive version of the number because, again, the table values represent the area between the mean and the z-score, and the distribution is symmetrical. So the area between negative 0.5 and 0 is the same as the area between positive 0.5 and 0 because it is perfectly symmetrical. So here is 0.5 on our table, and we don't have another decimal place. It's 0.5 even, so 0.50. So there is the probability between the mean and the z-score of negative 0.5, 0.1915. Okay, so now let's draw a diagram. And in doing the diagrams using these in doing calculations using these probabilities, where I was going with this is I always encourage you to draw a diagram to help you think through the calculation. So here is our z-score of negative 0.5. It's below the mean. And we're trying to find the percentile rank. So the probability of having a z-score below this area here under the curve, if the entire curve is 100%. What percentage of the curve falls below a z of negative 0.5? Now, what we've looked up, this 0.1915, is this area in here, the area between the z-score of negative 0.5 and the mean. So what could we do here in order to figure out the area below a z of negative 0.5? And I'm going to ask for somebody other than Sarah to take a crack at this.
We can do 50% minus 19.15%. So 0.5 minus 0.1915.
Good. We can do 0.5 minus 0.1915. So this entire half of the curve, once again, is 0.5. It's half the curve. And if we subtract off the piece in here, which is not what we want, but it is what we looked up, 0.5 minus 0.1915 gives us 0.3085. So the area below the z of negative 0.5 is 0.3085. I don't suggest you try to memorize how to do these different calculations if you have a positive z-score versus a negative z-score. I suggest you draw the diagram and think it through logically, keeping in mind that half the curve is 50%. So what chunks are you trying to put together or subtract off of 50%. So to interpret this information, what we can see is that Sean's percentile rank is 30.85%. That is about 31% of people have an SAT score of 950 or below, less than half, because he does have that negative Z-score. How does that example feel? Seeing nodding heads. I'm seeing at least some thumbs up. Good. Let's do one more example. And this one will be a little bit of a different probability calculation, not actually a percentile rank, but we will do much the same thing. So verbal scores on the GRE, the Graduate Records Exam, are normally distributed with a population mean of 500 and a population standard deviation of 100. What percentage of people would score between 300 and 700 on the verbal portion of the GRE test? Okay. Here we have two scores of interest. So when we identify our information, again, we have the population mean of 500, the population standard deviation of 100, and two scores of interest. We're going to call them X1 and X2, 300 and 700. Take a moment on your own and calculate the two Z-scores for this particular scenario. And yes, I have chosen nice, easy numbers for you to work with. No calculators required. Okay, what do we have? May I have a volunteer to tell us the two Z-scores?
2 and -2.
Good, 2 and -2, thank you. So when we convert the scores of interest to Z-scores, for Z1, we had to have 300 minus 500 divided by 100, so -2. For Z2, we would have 700 minus 500 divided by 100, +2. Now, what's nice here is because we have the same absolute value, there's only one number we have to look up in our Z-score distribution, because of course the curve is symmetrical. So the area between the Z-score and the mean will be the same for the positive Z-score as it is for the negative Z-score. So let's go ahead and do that. So here's what we're going to try to find. We are trying, and I apologize for the difference in this picture. It was the best depiction I could find. But we are trying to find the entire area between a Z-score of -2 and a Z-score of +2. Who can go to their Z table and find the probability associated with a Z-score of 2? It's in the back of your notes. Take a look. .0. Who has the probability?
I can go.
Hey,
It's
Sarah, thank you.
0.4772.
Good. The area between the mean and a Z-score of 2, and this is both the light blue and the dark blue parts here, between the mean and a Z-score of 2 is 0.4772. Now, of course, the curve is symmetrical, so to find the other side, it's also 0.4772. So we simply have to either multiply by 2 or simply add 0.4772 plus 0.4772. And we would find that together, it's 0.9544. So the area between a z-score of 0 and 2 standard deviations above the mean is 47.72%. The area between 0 and 2 standard deviations below the mean is 47.72%. So altogether, 0.9544. So when we interpret this, we see that about 95.44% of people would score between 300 and 700 on the verbal portion of the GRE. Questions there? Does everybody see how we're manipulating these numbers from the table? Okay. I realize that this is the end of this particular set of notes, but there's one more thing I would like to share with you. It's just some useful numbers to remember. We just calculated the percentage of scores that fall within 2 standard deviations of the mean, and it is right around 95%, as is shown here. So here are the numbers that are useful to remember. About 2/3 of people, 68%, which is just above 2/3, but about 2/3 of people fall within 1 standard deviation of the mean. 95% of people fall within 2 standard deviations of the mean on any given normal measure. And over 99%, 99.7% of scores fall within 3 standard deviations of the mean. So just useful things to remember. Just over 2/3 within 1 standard deviation, 95% within 2 standard deviations, and 99.7%, over 99% within 3 standard deviations of the mean. Next day, we're going to move this forward and we're going to see how these ideas of probability calculations apply to those inferential statistics. How we can go from simply describing our data to making inferences from our sample to our population. But that is our story for next day. So I'm going to stop it there. And we will be moving into office hours today a few minutes early. So have a good few days, and I will see everybody either in my office hours on Friday, if you would like to do a check-in, or next Monday for class. Take care, everybody.